Welcome in, everyone. We're diving deep today into a systematic review of robustness in deep learning for computer vision. Mind the gap. This paper really struck me as tackling a crucial issue, and, well, I'm keen to unpack it with you.
Yeah, definitely. It's super relevant right now, especially with deep neural networks becoming so central to computer vision. The problem of image corruptions and how vulnerable these systems are. It's a big one, especially if we want to use them in the real world, right?
For sure. Like, we all know DNNs can hit incredible accuracy in the lab, beautiful, pristine data sets, all that. But the second those images get tweaked, even a tiny bit, corrupted in some way, the performance can totally tank.
Exactly. And this paper, that's what it digs into, this gap between how well things work in a perfect setup versus out there in reality. And it's not just about the adversarial attacks that get so much attention. They're looking at like the naturally occurring stuff, the changes that just happen, rain, blur, even like compression artifacts, you name it, real world things.
Yeah, the everyday messiness of reality. Not just some intentional attack, but the stuff that just happens when you're capturing an image. Makes a lot of sense.
Yeah.
But what makes this paper stand out from all the other work on robustness? What's the hook?
One thing that really jumped out at me was their focus on causality. They're pushing for a more rigorous, thought out approach to robustness. And to do that, they suggest using a structural causal model, or SCM for short.
Okay, now let's break that down a bit. What is an SCM in this context specifically? And how does it help us think about robustness in a more well-defined way?
All right, so picture it like a chain of events, right? A whole series of things that have to happen for an image to exist. You start with the scene itself, whatever's being photographed. Then you've got the sensor, the camera capturing it. And finally, any processing that gets done to that image compression, for example. Each of those steps, they can introduce little variations into the final image.
Oh, I see. So like if it's snowing on the scene, that's an environmental factor.
Got
But
it.
then sensor noise, that's coming from the camera itself. And if you save the image as a JPEG, you're going to get those compression artifacts.
Exactly. You got it. And by linking those corruptions to specific parts of the SCM, it gives us a much clearer picture. Not just what's causing the problem, but how likely it is to actually mess things up.
So it's adding context,
Mhm.
right? It's not just, oh, there's blur, but this blur probably came from the lens, and here's how much we should worry about it.
Right. And this feeds into one of the paper's main critiques, that a lot of the benchmarks we use now, they rely on these artificially generated corruptions. And they don't always consider how likely those corruptions are to actually happen in real life.
So a model could be amazing at dealing with some super specific synthetic blur, but then totally fall apart when it encounters motion blur from a moving camera in the real world.
Yeah, precisely. The SCM framework is kind of pushing us to say, hey, let's move past these fake scenarios and think about the corruptions that are actually going to matter out there.
That's a really good point. So we've talked about the problem itself and the SCM framework for thinking about it. But this paper also dives into how robustness is defined and measured. What did they find when they looked at all these different studies?
It's funny because the word robustness, it gets thrown around a lot, but what
Yeah.
they found is a lot of studies don't even clearly define what they mean by it.
Oh, that's a problem.
Yeah.
So researchers could be talking about the same thing, but measuring it in totally different ways. How do you even compare results then?
Exactly. It's a mess. The paper highlights a few metrics that try to quantify robustness, each with their own pros and cons, of course. Things like mean corruption error, MCE, relative corruption error, RCE, and robustness score.
I think our listeners are probably familiar with those, but a quick refresher never hurts, just to get everyone on the same page.
Sure thing. So MCE, that's your average error across a bunch of different corruptions. Then you've got RCE, which compares how the model performs on corrupted images versus clean ones. And the robustness score, that takes both the accuracy and the severity of the corruption into account.
So these metrics give us a way to put a number on how much a model's performance actually degrades when it sees those messed up images. But I'm guessing there's some limitations to these too, right?
Oh, absolutely. One thing the paper points out is that most of these metrics, they don't consider how likely a certain corruption is to actually happen in the real world. They kind of treat them all equally, which that's not really realistic.
So even if a model has a super low MCE across a bunch of corruptions, it can still be super vulnerable to one specific type that's really common in the environment it's going to be used in.
Yeah, exactly. And that's another reason why this whole SCM framework is so valuable. It's telling us, hey, let's get specific, stop looking at just generic benchmarks and start thinking about the corruptions that are actually going to matter in this particular application.
Makes sense. Okay, so we've laid out the problem, how to think about it with the SCM. and the ways we've been trying to measure robustness with their limitations. But what about solutions? The paper talks about three main tactics to try and improve robustness: architecture, data augmentation, and optimization. Let's start with architecture. What are some of the interesting approaches there?
All right, well, there are some cool ones for sure. One that pops to mind is a Von block. It's actually inspired by, get this, the visual system of primates, like
Yeah.
monkeys and stuff.
Oh, yeah, I remember reading about that. It uses Gabor filters, right? Which are known to be really sensitive to edges and textures.
Yeah.
And it incorporates some randomness, some stochasticity, to make the model less fixated on very specific pixel values.
Exactly. So it's like trying to mimic how our brains process visual info, which is inherently very robust, right? And even though it wasn't designed specifically with image corruptions in mind, it's showing some really promising results in that area.
That's cool. Taking inspiration from biology, from how our own brains do it, seems like that could be a really fruitful direction, you know? What other trends in architecture stood out to you?
Another big one is the rise of what they call spectral approaches. So this could be stuff like incorporating anti-aliasing techniques or using wavelet-based layers in the model. The basic idea is to prioritize the low-frequency information. That tends to be more resilient to noise and other corruptions.
Ah, so instead of getting caught up in all the little details, these models are learning to pick out the big picture, the overall shapes and patterns, which are less likely to be totally messed up by those pixel-level changes.
Exactly. And it makes intuitive sense, right? Like if you look at a blurry picture, you can usually still tell what the objects are, what's going on in the scene, even if you can't make out all the fine details.
Right, we don't get thrown off by a little blur in real life. So these spectral approaches are trying to replicate that, I guess, that human ability to focus on the essential information.
That's a great way to put it. It's like giving the model a more holistic view rather than getting bogged down in all the noise. And that's a really promising direction for building architectures that are just inherently more robust to real-world conditions.
So we've covered some interesting architectural approaches.
Uh,
But what about data augmentation? Seems like everyone's doing that these days to try and make their models more robust. What's the deal there?
yeah, data augmentation is definitely a hot topic. Basically, the idea is to expose your model to a wider range of image conditions during training, try to make it tougher, more resilient to the corruptions it might run into later.
Kind of like giving it a crash course in the messy reality of real-world photography, right?
Yeah.
Instead of just feeding it those perfect, pristine images.
Exactly. And the paper goes through a bunch of different techniques, including mix-up and some of its variations like puzzle mix and smooth mix.
Oh yeah, I'm familiar with mix-up. You're basically like blending different images together, right? And their labels too. Is the idea there to force the model to learn smoother decision boundaries so it's not so thrown off by little changes in the input?
That's the gist of it. It's trying to teach the model, hey, even if the image changes a little bit, the core content is still the same, don't freak out, which makes sense for dealing with corruptions where the main stuff in the image is still there, just maybe a bit degraded.
So it's like teaching it to see the forest for the trees, not get hung up on every little pixel, but focus on the overall meaning. But there's got to be some limitations to this approach, right? You can't just infinitely blend images together and expect miracles.
For sure. The paper points out that even with these fancy augmentation techniques, the robustness gap isn't completely closed. Plus, generating all these augmented images, it can be computationally expensive, especially when you're dealing with massive data sets.
And then there's the question of realism, right? How well do these augmentations actually reflect the full range of corruptions that you see in real-world data? It's one thing to mix up some images in a controlled way, but reality's got a lot more tricks up its sleeve.
Yeah, that's a valid point. It's an ongoing challenge to make sure your augmentations are actually representative of what the model's going to face out there in the wild. If you just rely on these synthetic ones, it might be robust to those specific types, but then totally fail when it sees something it's never encountered before.
Yeah, it's like training for a marathon on a treadmill and then being surprised when the actual race throws in hills and wind and a bunch of squirrels running across the path. So data augmentation's a good tool, but it's not a magic bullet. Okay, let's move on to the third tactic. Optimization. What can we do during the actual training process to bake in more robustness?
So optimization, that's all about tweaking the learning process itself to make the model more resilient. And one of the big ones that comes up is adversarial training.
Yes, the classic fight fire with fire approach. You're basically pitting your model against an adversary that's trying to trick it, right?
Yep, that's the idea. By throwing these adversarial examples at the model during training, You're forcing it to learn features that are less susceptible to, being intentionally manipulated.
So it's constantly being challenged, having to figure out more robust, more generalizable features that can't be so easily exploited.
Yeah.
What are some of the specific adversarial training methods they highlighted in the paper?
There's a few interesting ones. One is like learning a noise distribution. So you train the model on data with different levels of, carefully crafted noise. And another is entropy maximization, where you're kind of pushing the model to learn a more diverse set of features so it's not so easily fooled.
It seems like the goal with all of these is to prevent the model from overfitting, right?
Mhm.
Like you can't just memorize specific clean examples anymore. It's got to learn representations that are more uh, stable, more resistant to any kind of perturbation, whether it's adversarial or just naturally occurring.
You nailed it. And the paper also touches on some other cool optimization techniques, like there's regularization methods inspired by how the brain works, and structured dropout strategies, and even some contrastive learning methods.
A whole smorgasbord of tools in the optimization toolbox. But one thing I was curious about, the paper didn't just focus on new methods, right? They also looked at studies that were evaluating how robust existing models are. What did those reveal?
Yeah, there were a bunch of studies that just took like state-of-the-art models and threw various types of corruption at them to see how they'd hold up. And, the results are kind of eye-opening.
I'm guessing it wasn't all sunshine and roses.
Not exactly. Pretty consistently, these studies found that even our best models, they take a pretty significant hit in performance when you introduce corrupted data. Noise, especially, seems to be a real Achilles heel for a lot of these architectures.
So even with all the progress we've made in deep learning, this robustness thing is still a major hurdle, especially if we want to use these models for like real-world tasks where safety is a concern.
You got it. And that's why this paper is so important. It's bringing this whole issue to the forefront, showing us where the gaps are, and urging the community to really prioritize research in this area.
So coming back to that initial question from the paper's title, Mind the Gap, is there really a robustness gap in deep learning? Like, are we just making a mountain out of a molehill here, or is this something we should actually be worried about?
Based on what this review presents, I'd say the gap is real and it's not small. We've made progress, sure, with architecture, data augmentation, optimization, but there's still a big difference between how well these models perform on those clean benchmark data sets versus how they handle the messy reality of real-world images.
That's a sobering thought, but important to acknowledge. So for researchers and practitioners out there working with deep learning, especially in computer vision, what are the key takeaways? What should they be keeping in mind as they go forward?
Well, a few big things stand out. First off, just throwing more data at the problem, bigger data sets, that's not going to cut it. We need to move beyond these artificial benchmarks and come up with more realistic evaluation methods that actually reflect the types of corruptions and how likely they are in specific applications.
So kind of echoing that whole SCM framework we talked about earlier, understanding the WHY behind the corruption, not just the what.
Absolutely. The paper also suggests we need to start thinking beyond just these static models, maybe dynamics models, the ones that can actually adapt to changing conditions. Those might be a more promising path toward true robustness.
That's an interesting thought, a model that can kind of like adjust its internal workings based on the input it's seeing. If the image is super clear, maybe it can be more sensitive to the details. But if there's a lot of noise or blur, it can shift to a more big picture view.
Precisely. It's like giving the model the ability to switch its glasses depending on what kind of visual environment it's in.
Makes a lot of sense. All right, before we start looking ahead to like what the future holds, let's do a quick recap of this paper's core findings, just to make sure everyone's on the same page.
Okay, so to sum it up, this paper clearly shows that there's a big robustness gap in deep learning for computer vision. Our current models, they're just not as good as we'd like them to be at handling these naturally occurring image corruptions. And that has some serious implications for real-world applications, especially in areas where safety is a big concern.
Right, and they're arguing that we need a fundamental shift in how we're approaching this whole robustness thing. We can't just rely on synthetic benchmarks and these oversimplified metrics anymore. We need more realistic evaluations. We need to understand the causal factors behind the corruptions. And maybe we even need to start looking at these dynamic models that can adapt on the fly.
And a really important point they make is that, this isn't a solo mission. It's going to take the whole research community working together, prioritizing robustness, exploring new architectures, new training methods, new evaluation strategies. That's how we're going to bridge the gap between how well things work in the lab and how they actually perform out there in the wild.
It's a call to action, a challenge to really think differently and push the boundaries of what's possible with deep learning. This paper has definitely given us a lot to chew on.
It has, and it leaves us with a pretty provocative question. What are the alternative paths forward? If bigger data sets aren't the answer, what else can we do to achieve true robustness in deep learning for computer vision?
That's the million-dollar question, isn't it? Where do we go from here? The paper gives us a few hints, but it feels like we're just starting to explore this whole area.
Yeah, I'd agree with that. There's so much we don't know yet, so much room to experiment and try new things. And honestly, I think one of the most promising avenues is to look outside of computer science to fields that have been grappling with these ideas of robustness and generalization for much longer than we have.
You're talking about, like, neuroscience and cognitive science, right?
Right.
Trying to understand how biological systems, like our brains, handle all this complexity and variability that we encounter in the real world.
Exactly. Our brains are incredibly robust, right? Think about it. We can recognize objects even if the lighting changes or the viewpoint's different, or even if part of the object is hidden. We adapt to new environments, learn new skills constantly throughout our lives. There's a goldmine of knowledge there that we can learn from.
So instead of just focusing on deep learning and isolation, we can start to build bridges between artificial and biological intelligence. Learn from the ultimate robustness expert, Mother Nature herself.
I like that. And the paper does touch on a few areas where this kind of cross-pollination of ideas could be really fruitful. One of them is this concept of lifelong learning.
Oh yeah, the idea that models shouldn't just learn from one fixed data set and then call it a day. They should be able to keep adapting, keep updating their knowledge as they encounter new data, just like we do.
Right. Imagine a deep learning model that can actually identify its own mistakes, learn from them, and get better over time. That would be a huge step toward true robustness.
How we learn, right? We're constantly refining our understanding of the world based on new experiences.
Ah.
What else can we learn from neuroscience? What other insights could help us build more robust deep learning systems?
Another big one is understanding how our brains actually represent and process information. We know that the brain uses these sparse representations, which basically means that only a small fraction of neurons are active at any given time. And it relies heavily on attention mechanisms, focusing on the most relevant information and filtering out all the distractions.
So it's not just about the size of the model or even the amount of data you throw at it. It's about how it's representing that data, how it's processing it. Efficiency and selectivity, those seem to be key.
Absolutely. And this is where a lot of current deep learning models fall short. They tend to be very dense, very computationally expensive. Maybe by incorporating these ideas of sparsity and attention, we can build models that are not only more robust, but also more efficient, more energy saving.
It's mind-blowing to think about how we can translate these biological principles into actual, architectural and algorithmic innovations. The paper also mentions briefly the idea of prior knowledge and how that plays into robustness. Can you expand on that a bit?
Sure. So right now, most deep learning models, they start with a blank slate. They don't have any pre-existing knowledge about the world. They just learn from the data they're given. But us humans, we come preloaded with all this prior knowledge, right? Stuff that's built up through evolution, early experiences, all that. And that helps us learn faster, generalize better to new situations.
We're not just pattern matching machines, right? We have this underlying understanding of physics, causality, even social dynamics that shapes how we learn.
Exactly. And the paper suggests that incorporating this kind of prior knowledge into deep learning models could be a game changer for robustness. Like maybe we can embed explicit rules or relationships into the model, or use pre-training on data sets that capture relevant concepts.
So instead of starting from zero, we can give the model a head start, a set of basic principles to work with. It's like building a scaffold for learning, helping it to learn more efficiently and avoid learning spurious correlations.
Right. And this ties back to the importance of causality that we talked about earlier. If we understand the causal relationships in the data, we can encode prior knowledge that actually reflects how the world works. And that should lead to models that are not only more robust, but also more interpretable, more trustworthy.
It's a really exciting direction for research. and it shows how important it is to collaborate across different disciplines.
Mm.
We need computer scientists working with neuroscientists, cognitive scientists, experts from all these different fields to really unlock the potential of this approach.
I couldn't agree more. And I truly believe that by pursuing these paths, drawing inspiration from biology, incorporating prior knowledge, and constantly pushing the boundaries of what's possible with architecture, training methods, and evaluation, we can make significant progress toward achieving true robustness in depth learning, especially for computer vision, which has so much potential to impact our world.
It's a big goal, for sure, but a crucial one. We need to build models that we can trust. They can handle the complexity and unpredictability of the real world, and it's conversations like this that help to move us in the right direction.
Absolutely. This paper has been a great starting point, laying out the challenges and pointing toward possible solutions.
Well said. Thanks for joining me for this deep dive. It's been a fascinating exploration of a topic that's really at the heart of AI's future.
The pleasure was all mine. And for our listeners, keep exploring this area, keep asking questions, keep pushing the boundaries. We need all hands on deck if we're going to build truly robust and reliable AI systems.